He's wearing well, isn't he, old Chris Packham? He'll be 58, you know, on the 4th of May. May the 4th be with you, Chris. Anyway, I don't know if this goes out around the world, but it's called Blue Planet Live. If you can find it, I recommend you watch it because it's basically a week's worth of programmes taking a health check of our oceans. I recorded this little snippet from Sunday's programme because Packham made a really good point.
Do you know, I've been sat here and I've been looking out of this lagoon into the Pacific Ocean and I've been thinking to myself, we give all of these oceans different names, Atlantic, Pacific, Indian, but there are no fences between them. They're all joined up. And as a consequence of that, all of the ecosystems that we've been looking at and enjoying today, all of these fantastic animals are connected to one another. They're dependent upon one another. And ultimately, our health and our future is dependent on them as well. What a program.
And that reminded me that I haven't really yet got to grips with how all that works. So brace yourself, friends, because this week I'm going to apply my considerable ignorance and incompetence to the task of understanding the thermohaline circulation. Hello and welcome to Just Have a Think. A couple of programmes ago I touched on the possibility of a September ice-free Arctic in the coming years, something that's become known as a Blue Ocean Event or BOE, and I made a note to take a close look at what would be the consequences if that happened. But in order to do that, I first really need to get my mind around all the complicated interactions of driving forces and currents in our oceans, and it turns out that that is a science fest of technical terms, abbreviations and acronyms. So here goes. Thermo is from the Greek word thermos, which means heat. Haline comes from the Greek word for saltiness. Now we've obviously got English words for these things, but I guess the scientists figured that the hotty salty circulation was probably not appropriate, so thermohaline it is. In fairness, it's actually sometimes also referred to as the ocean conveyor belt, the Great Ocean Conveyor, or the global conveyor belt. So how does it work? Well, let's start with the surface currents. According to Wikipedia, the movement of surface currents pushed by the wind is fairly intuitive. For example, the wind easily produces ripples on the surface of a pond. Thus, the deep ocean, devoid of wind, was assumed to be perfectly static by early oceanographers. Idiots! Nowadays, of course, our scientists have all sorts of fancy instruments and contraptions which show quite clearly that there are significant currents in the depths that can move as quickly as 1 metre per second. The main driver for these currents is differences in water density, which are driven by temperature and salinity. Warm water expands, so the water at the top of the ocean, which is warmed by the sun, is much less dense than the cold water at the bottom of the ocean. Salt makes water more dense because the salt actually fills up the gaps between the water molecules, so you get a higher density for the same volume of water. Here's America's favourite pretend wacky scientist, Bill Nye, showing us how salty water sinks below fresh water.
Bill Nye the Science Guy.
Now the more salt in the water, the heavier it is. So it sinks. See?
Nice one, Bill. So up here in the northern latitudes of the North Atlantic, warm water from the Gulf Stream arrives, driven largely by the wind. When it reaches here, it gets cooled by the generally cold temperatures of the ambient air and also by the cold winds that blow around in the region. As that wind whistles over the surface, it causes a lot of the water to evaporate for reasons that are outside the scope of this video, but that evaporation only takes the water molecules, not the salt in the water. So the seawater that's left behind gets more salty and more dense, and that makes it sink. Scientists call this the North Atlantic deep water, which seems reasonable. I should say here that other seas also feed the North Atlantic deep water. For example, the Labrador Sea off the coast of northeastern Canada, where the cold water sinks to depths of 3,000 metres at a rate of 10 centimetres a second. Anyway, when all this cold, dense water hits the bottom, it spreads out. It can't really go up into the Pacific from here because the Bering Strait's too narrow, so it takes the course of least resistance, which is southwards, very slowly into the depths of the Atlantic, flowing down around South Africa, where all sorts of exciting things happen. The deep water travels right down to Antarctica, where it gets caught up in the most powerful current on the planet, the Antarctic Circumpolar Current, moving about 140 to 180 million cubic metres of water per second in a rotation around the icy continent. Down here in Antarctica, a really important process occurs known as overturning. Oceans have layers. The top layer is about 100 metres deep and gets enough sunlight for organisms like phytoplankton to do photosynthesis. And phytoplankton are of course the first stage of the ocean food chain and absolutely essential to all ocean life. As phytoplankton die, they sink and collect on the ocean floor. In Antarctica, the freezing cold surface water sinks, and as it sinks it forces the nutrient-rich deep water to rise. Overturning at Antarctica moves about 35 to 45 million cubic metres of water every second from the ocean bottom to the surface in a sort of gigantic tumbling rotation. So the Antarctic Circumpolar Current, combined with this nutrient bonanza from the overturning process, makes the waters around Antarctica an ideal habitat for marine mammals. Many types of whales migrate there every year to feed on phytoplankton and other tiny sea creatures churned up by the overturning waters. So it's a vital part of the ocean ecosystem. Anyway, back to our circulation journey. Parts of the circumpolar current flow northward and move towards the Pacific and Indian Oceans, where a gradual warming occurs as the two bodies of water mix. This results in another effect called upwelling, which once again causes the rich deep sea nutrients to be brought to the top layer of the ocean. This top layer warm water then flows back around the southern tip of Africa and into the Atlantic to continue the circuit up into the Arctic once again. And here's my favourite statistic of the whole thing. It takes about 500 years for the conveyor belt to turn over the ocean's waters and make one complete circuit around the planet. So I think we can say that science has established that this system is an absolutely crucial supplier of nutrients to the ocean food chain and a redistributor of heat around the planet. Now at this stage, some of you are probably wondering why I haven't made any mention of AMOC, which is the Atlantic Meridional Overturning Current. That's the one that featured in the 2004 film The Day After Tomorrow. Thermohaline circulation and AMOC are terms that are often used interchangeably in papers and articles. But as far as I can make out, and help me out here folks if I've got this one wrong, strictly speaking, thermohaline circulation is driven purely by the differences in temperature and salinity that we've just looked at, whereas AMOC refers to the entire overturning circulation of our oceans, driven both by the deep water currents and by the top surface currents, predominantly driven by the wind. So they're pretty close, but they're not exactly the same. And then on top of both those things, we've also got the not inconsiderable effects of the Gulf Stream, which is connected to the overall system, but again, strictly speaking, not part of the thermohaline circulation. The Gulf Stream starts in the Gulf of Mexico and follows the eastern coastlines of the United States before crossing the Atlantic Ocean. It flows at a speed of about 6 miles an hour at the surface, and as it makes its way north, it passes very close to Europe. There appears to be a reasonable scientific consensus that this warm water flow past the shores of Europe is a major contributory factor in the continent remaining on average about 5 degrees Celsius warmer than areas of Canada that are at exactly the same latitude. Recent articles such as this one in The Guardian from April 2018 reported evidence suggesting the Gulf Stream is at its weakest in 1600 years and that the consequence of this may be a significant cooling effect on Europe's climate. The report told us the warm Atlantic current linked to severe and abrupt changes in the climate in the past is now at its weakest in at least 1600 years, new research shows. The findings, based on multiple lines of scientific evidence, throw into question previous predictions that a catastrophic collapse of the Gulf Stream would take centuries to occur. And it goes on to say, such a collapse would see Western Europe suffer far more extreme winters, sea levels rise fast on the eastern seaboard of the US, and would disrupt vital tropical rains. The new research shows the current is now 15% weaker than around 400 AD, an exceptionally large deviation, and that human-caused global warming is responsible for at least a significant part of the weakening. While the threat to the eastern seaboard and the tropical rains may be very real possibilities, Some climate scientists are starting to find that the very thing that causes the Gulf Stream to slow down, human-induced climate change, might also, ironically, be minimising its impact, at least across in Europe. This report from the BBC, published in July 2018, looks at a paper by Professor Kit Tung of the University of Washington. The report tells us, while the waters in the North Atlantic will definitely cool as a result of changes in the flow, the experts say it's likely that the UK will see continued impacts of climate change over the next 20 years, according to this study. The air temperatures globally will be warming, and there's no barrier for that, so there won't be much cooling in the UK. You'll probably still see the normal global warming, said Professor Tung. Tung's theory is that the speed of the AMOC circulation may be cyclical in nature, maybe over decadal timescales. He says, when the current is faster, more of the warm, salty tropical water travels to the North Atlantic. Over years, this causes more glaciers to melt, and eventually the fresh water makes the surface water lighter and less likely to sink, slowing the current. And that gives us a sort of self-regulating cycle. Teng tells us when the AMOC was at a minimum between 1975 and 1998, more heat entered the atmosphere and global temperatures gradually went up. When the current started to accelerate from the mid-1990s to the early 2000s and sink more heat, it coincided with a so-called slowdown in the pace of global warming. Now, the authors of the paper say that the slowdown in AMOC since 2004 means less heat going into the sea and more heat going into the atmosphere, which is just about the worst coincidental timing we could possibly have, given the amount of global warming we're causing through our human CO2 emissions. But if Teng's theory is correct, then the cycle will shift and eventually the AMOC will start accelerating again. And surely that'll mean that more heat from the atmosphere is sequestered down into the depths of the ocean, and that'll bring some relief in the global temperatures, right? But what if something happens to stop it speeding up again? Just as a reminder of how complex and intricately interconnected our global life support system really is, let me leave you with the abstract of yet another scientific research paper. This one a senior thesis presented to the faculty of the Department of Geology and Geophysics at Yale University by Holden Leslie Bowl, Alexei Fedorov and Mary Louise Timmermans on the 2nd of May 2018. As anthropogenically forced climate change intensifies, the loss of Arctic sea ice will become an important factor affecting global weather and climate patterns. In particular, it's been shown recently that Arctic sea ice decline can contribute to the slowdown of the Atlantic meridional overturning circulation, which modulates climates not just in the Atlantic but globally. And that's why, as I mentioned earlier, in an upcoming programme I'm going to be having a look at the threat of a blue ocean event up in the Arctic. That's it for this week though. I'm going to go and have a lie down to let my brain cool off a little bit. Please do give us a like and a share if you found the programme useful, and if you haven't already done so, you can subscribe to the channel to get all the latest content. Doesn't cost you a thing to do that, you just need to click that link there. As always, thanks very much for watching, have a great week, and remember to just have a think. See you next week.